So I'm also going to talk about hardware acceleration. And I have a long talk, so I'll start quickly. So in Mellanox, we see two kinds of acceleration. First, acceleration, the Mellanox name is ASAP, Accelerate, Switch, and Packet Processing. So we divided the world to two options. As you can see on the left side, it's called ASAP Direct. It's then when you have virtual function that's directly connect to a virtual machine. And the OVS itself still managing everything, but the data path is going directly to the virtual machine. I'll describe it more later. And the second option, we call it ASAP Flex because it's more flexible. And in that, what has happening, we're running a standard OVS with virtual interface. And what we are doing, we're just accelerating the OVS that is running. Of course, we design it first for OVS DPDK, because it's the faster one. And I will describe it more later. So I will start with the direct. As I said, it's built of SRIOV. So what we did, we're talking about acceleration. So we don't try to take the OVS and run it on a different ARM kind of a server that is inside the NIC. What we're trying to do is to run the same OVS as before with the vSwitch D in the user space and the OVS data path in the kernel. But as the OVS is working, like the data path is moving faster, but doing the same action, logic action, as the user space, we're adding a kind of another layer, a hardware layer. So the vSwitch D can decide either you want to let the kernel forward the traffic, or even to let the hardware forward the traffic. So in that case, you don't see the packet, of course, in the kernel, and all the traffic is forwarded directly from the NIC, from the wire, to the virtual machine, or from the virtual machine directly to the wire. And everything is according to the rules and the configuration of the OVS, of the user space, the vSwitch D. So in order to do that, we work with all the communities, the Linux, the OVS community, and that was the end result. So what we did in the kernel, we implement the representer ports. That's we don't need to change the OVS, and then you connect them to the vSwitch to the OVS, and the rules from the OVS can, instead of going to the data path in the kernel, can go to the blue, the TC that is in blue, inside the kernel through the same code of this vSwitch D when it run in the kernel implementation. So we already done that. It's already in 2.8. And so if you're taking right now the OVS code, run a smart NIC, everything, it's not a vendor specific. You can use it also other vendors to do that. Of course, I recommend Mellanox. and it's work. So this is an upstream, as I said, it's upstream. It's not vendor lock. It's for the community. And of course, we did some tests to show what you gain from that. So when you took a single flow and you run OVS, of course, we don't want to compare to the kernel. We want to compare to OVS DPDK. So we done it a test for a VLAN, not a VXLAN, for the vSwitch, for the OVS DPDK. It's done not on a high-end server, but we got rough around 8 million packets per second. Of course, when you take the ConnectX-5, and we did the test for VXLAN, that will be much harder, and we get 66 million packets per second. And I think what is more important, you're getting this, it's a higher bandwidth, of course, But as you can see, the CPU is not doing nothing. The 4 cores that you use to drive the DPDK don't need. You can get them, let the orchestrator use them to have more VMs instead of tie them to do the job of forwarding the traffic. We also did some tests what happens when you have more flows. Of course, nobody uses 1 or 2 or 10K flows. Even 6K flows today, customer tells us, this is a good morning startup. It's not like a good number. It's something to start with. And then, of course, the OVS DPDK dropped down. Of course, we also have some, because it's happened because of all the cache misses. That's when you have a lot of flows. But the hardware is not dropping the same as the software implementation of OVS DPDK. And we even then reaching almost the 20 million packets per second. As I said, it's for VXLAN traffic. It's receiving, yes, you can see in the picture on the right. It's receiving the packet from the wire through the VN that's run test PMD, that's flip the max and send back the packet to the wire. So it's receiving and transmitting, of course. And again, no CPU used to do that. Of course, there are future work that's need to be done. So the recirculating things is not implemented yet. It's required, of course, for the connection tracking. We already push some patches to the TC interface to support recirculating. Now we need to implement it and to make OVS also use them. The second thing that we want to work on is connection tracking. As mentioned yesterday, we used, of course, it was last week we had a session on it in the NetDev conference in Seoul. The third thing that we are working right now is to support link aggregation, bonding for SRIOV, because you do want to go out. You want to have high availability and the virtual function to go out on 2 ports. And we're also trying to tackle and fix the issues and to support live migration, because this is the thing that all the customer complain that you don't support live migration for virtual function. So we hope also to fix that issue. We're working on that. So I will continue on ASAP Flex. As I said, we want to be flexible and just to accelerate the OVS DPDK. So as you're familiar with this picture, probably, there is the EMC and then the megaflows cache, megaflows rule, sorry, and that's how it's worked today. What we want to do is to have a kind of another layer before the exact match cache that stack all the rules from the megaflows. So to the hardware, we take the megaflows rules, not the exact match. And we tag the packets according to the rules. So for every megaflow rule, you get an ID. And when the packet hit this rule in the hardware tag this packet. So when the OVS DPDK is running, you get a metadata with the packet. And in order not to do and it's not required to do the classification of the packet, he just takes the metadata. So you don't need even to touch the packet. It's helping with the cache misses and everything, because you don't touch the buffer of the data. You know what's the classification of this packet. As I said, it's a megaflow rule. You'd go directly to the table of the megaflows rules. You know what the action that needs to be done. You're doing it, and you're done. So this is a kind of a layer that is done even before the exact match cache. And it's depend, of course, of the hardware. So our hardware can support millions of rules. So it's and it's millions of rules of megaflows rules. So you don't have to think, ooh, do I want to enable it, disable it, like what we're doing with the exact match cache. As we can see, it's suit not all the time. So that's the concept of the flex. But this is the first thing that we wanted to do. Of course, we want to do some offloads for other things. So it's not an RFC. It's already in the OVS mailing list. I think now we're supposed to send version 4 for that. It's sent by Yonhan. And we see the performance just getting with those classification offload. So as you can see, if it's a wire to VirtIO, we see a benefit of more than around 50%. And if it's wire to wire, we even see a more impact on that. It's 70%. And also here, when you can see that when you have a lot of flows, the performance is dropping down in the software implementation. And the hardware itself, you see a little bit drop from 11.7 to 11.2. So at the end, the improvement is much bigger. So you're welcome to look for those patches and to try them, of course. So I wanted to talk, and I had a talk in the OVS DPDK session 2 days ago, regarding how to implement also to accelerate the VXLAN. So the VXLAN in OVS is done in 2 levels. So you have the lower switch, BR Fizz, that's usually used in OpenStack. And then it's going to the VXLAN port. And in the data path, it's done like a recirculating. So you need to classify again the packet. So the method that I presented before, it just helps to accelerate the lower switch. And we want also to gain from the hardware to classify according to the tunnel switch. OK, so in order to do that, we need a kind of multi-table. So that's what we're doing in the hardware. We have a table. We classify. And the action before that we used before was to set a tag ID, a flow ID. And if the packet is not, we're not yet done with the packet, we know that you need to recirculate, reclassify again on the inner packet. So the action will be go to another table. And the other table, table number 1 here, will do another classification inside the thing. Everything is inside the hardware. And then you set a flow ID. But now it's mean that the flow ID mean that it's classify the first table, that send the packet to the second table, and then there it was classified according to the ruling. So it means that the flow tag there means that the packet cross all the required classification. So as I mentioned before, we use those two tables in order to doing the reclassifying, the recirculate that is done in the OVS itself. We hope, of course, that it improve. We did some tests, of course, and we see that's improving in another 50% the offload, the performance. And I think what is nice with that, it's just an acceleration. So the idea, the difference between Flex and SRIOV, it means that you still continue to work with the VirtIO. You can still have anything that you want in the data path. You just run in OVS DPDK, and you just give him some hint in order to hardware offload a part of the hard stuff that you need to do. Same. And I think we did, it's a few years of work that's now, I think, it's not come to an end, of course, it's in progress. So it's starting with a Linux, of course, community in order to support it inside the Linux. So we talk there, we present things in the Linux community. It was starting in, it started even before, but in NetDev 1.2 a year ago, we present the whole solution with the TC flower and everything, and it was accepted. In the Open vSwitch last year, I think this is the first time that the OVS community want to listen about hardware offload, because a few years before we get, we don't need it, you not support everything, blah, blah. We don't need it. And thanks for the community that's willing to accept the hardware offload. So, of course, we did the work in order to write the code for the OVS. It's 33 patches. It's kind of a long patches. That was submitted by Mellanox to support the hardware offload. Of course, from there are some fixes and more kind of hardware more offload that's we're doing there. In order to have a full solution for a customer, we already went, of course, to the OpenStack, because this is kind of mainstream today to do the things. So we pushed to the OpenStack the notion that you can have a virtual machine that have an SRAOV and use OVS in order to configure things. This was two different worlds in the beginning when we came there. So we need to send some patches, of course, to the Neutron, to the Nova, OS VIF. So all those patches, of course, after Bluefin and all the things, also was accepted. So if today you take an upstream kernel, OVS 2.8, upstream OpenStack, out of the box, put a Mellanox card inside, and everything is working. So this is for the direct implementation. And of course, we did it also for the DPDK. So we worked and we pushed the RTE Flow API. That's all the DPDK community now using. Before it was that every NIC support kind of a different flow, very, very specific to the according to the vendor. And we made some order there. That's everything will be NIC agnostic. So that's already been done for more than a year. And we also did what I mentioned before. This is not an RFC. It's already probably will be pushed in. The acceleration of OVS DPDK. As I want to also mention the Mellanox guy that's worked on it. As you can see, it's a lot of good people that's helped to do the things, all the patches and all the hard work. So I want to give the credit, of course, to them. And of course, we want to work on other things and to improve this API. And I think what I want to mention most is when we're talking about Mellanox, we talk about the standard NIC, the standard 25 gig NICs. It's not required to buy a fancy NIC. All our NIC are smart NIC. We don't have kind of dummy NICs. So when I talk about those acceleration, you can use them in ConnectX-4, ConnectX-4 LX, ConnectX-5. You don't need to mention that you want to use this feature and pay for that. So you are welcome to try it. Not at home, of course. I hope that you don't have those kind of networks at home. And that's all.
So we have time for some questions, but before we get into that, I want to say thank you to Rony and to your colleagues at Mellanox for getting that acceleration API into there, and to Joe Strenger for putting so much work into reviewing it. One of the things that impressed me is that a couple of days ago I was talking to someone from Broadcom about how they're using the acceleration API. And when I asked, so what changes do you have to make to OVS? Is there a patch series coming up? He said, you don't have to make any changes. It just works with the API, and it just works. So to me, that's an indication that it was designed right. So thank you.
Thank you.
So I think I spotted Bob first. So please go ahead.
So I really like the contrast between yesterday, which was all DPDK all the time, and today is like DPDK considered harmful, and we should do hardware offload. And so my question: it seems like we have a lot of different options with OVS. Either run OVS kind of as is, or burn an x86 core to offload a piece of it to DPDK, or offload or partial offload to hardware to SmartNIC, as you suggest, or full offload like Liquid IO. So my question for you is how do you decide which of these approaches is appropriate for your environment and application?
So it's according to the limitation, the requirement that you want to have. So I think, of course, everyone understands that the direct is the best way to do, because you don't need to spend any cores on your system. But then there are customers that say, OK, you don't support currently VAF migration, so it's out of the question to use the direct. There are other customers that saying, but I want to do, that's all the packets, I have a secret thing that I want to do in the DPDK. So they also can't use the direct. So my first recommendation is go for the direct, better performance, less CPU, zero CPU, that's the best. But if you have requirement like a contract is not supporting today in the hardware offload, so if you want to implement today and you want to have security group, you can't use the direct. So that's the reason there is also the flex, the ASAP flex, that you can continue to use the OVS DPDK. It's work and support all the things that OVS is doing today, and just can accelerate the performance. So it's depend. So it's not one size. One size not fit all. As you can see, I can't fit in one size shirt.
All right, yeah.
Yes, almost answered my question already. But assuming we can fix all the feature gaps between the different options, from a performance perspective, how do you see the direct offload compared to the classification offload with DPDK? Will they be close, or will there be a significant difference in the future?
So you're talking about the performance, or you talk about from a feature perspective?
I was assuming that you and everybody else here we are managing to fix the feature gaps, so that in the future we have contract here and there and everything. And
so I think what is different in Mellanox, the card it's a SmartNIC, but it's not a CPU based. So it's a silicon base. That's the reason the performance and the power, of course, is much better. So it will take time to close all the gaps. And the performance of the Flex, it's always be less, of course, because you still have to do some job in the hypervisor, and you need to spend some core in the hypervisor to do that. So I'm not sure that's at the end, probably the Flex, if you're talking a few years ahead, I think that's the obvious DPDK will be less important.
All right, we're out of time for questions, so let's thank our speaker again.
Yep.